Hello everyone, this is going to be our lecture 5. I think last time I was a little too optimistic. My lecture 4, the first slide I had template functions, pointers, and classes. Um, we didn't really make it, we did have recursion in there as well, but we didn't really make it all the way through pointers, let alone classes, right? So we didn't even get there. This lecture, I'm hoping to wrap up pointers and then take a deeper look at classes. We might go further, but let's see. These are the two topics I planned out, and we'll see how far we get into it. So, last time I did touch upon this, right? The increment of pointers, the decrement of pointers, doing some sort of calculation basically with these pointers. And it made sense in the concept of an array. Um, Now I am going to walk through an example, um, and then so here, last time I had an array, and instead of using the index of the array, I used the index of the pointers to output the what's in there, right? Now this time, I've got an array, right, of three elements, and I've got an integer pointer that's pointing to the array, and then I have a for loop. Watch what's happening in the for loop. The for loop goes from 0 to till 3, right? So 3 times it's going to go into the loop. And every time it's in there, it's going to say what's the pointer. So what's that address in the memory? And then what's the value in it? And then PTR plus plus. So when you do this PTR plus plus, what are you doing? Think about it. You're incrementing what's in PTR, right? PTR is nothing, just a memory address. And when you increment it, it's going to go to the next element. I ran it here. I'll run it again. See, every time you've incremented PTR, 388, 38C, 390, the memory got incremented. And what was add the memory? The first element was 10, the second element was 100, and then the third one was a 200, right? So you're incrementing the memory address, and then you're making it move to the next address. In this case, these are the three elements, and that's how we go through. There is also, there's just also a concept of void pointer. Why a void pointer? Think of a void pointer as a generic pointer. You've got those template T, right? So here in this we have a void pointer. You can uh, have the void pointer point to pretty much anything you want. So I've got a method called increase, and then that takes in a void pointer called data, and then a size. And then what it says if this size is the size of a character, then I declare a character pointer, right? Typecast this data to a character, increase the character stored by 1. So when you do star at PTR, you get the value. So I put parentheses and I increment. So I'm incrementing the value at star PTR. And then I say data points to this character. Otherwise, if it's an integer, I typecast PTR ptrint to integer, and then I increment that integer. And then I have a character and an integer defined. And the first time I call, and this is called by value, and this is called by reference. This is called by reference method. Because you see increase, it says ampersand C, and then size of C, and then ampersand I, size of I. What happens? So first time when you've called it with a character X. It's gonna say it should be in here, right? Size of a character. Now you increment whatever the pointer was pointing to. It was pointing to X. Well, the new value of C is Y. What happened there? Because you incremented by 1. Now for the next time. Ampersand I, size of I. What's going on over there? You're sending an I, which is an integer, which is 10. So it's going to come in here. If it's size of an integer, you declare an integer pointer, and then you cast the data to int, and then you increment that by 1. That's the reason you see 11 here. Make sense? Okay. Let's keep going. Now there are two other things that I should touch upon, which are important, and you'll run into this quite often. One is an invalid pointer that you have this dangling pointer. I don't think the book mentions it, but I'll keep calling it invalid pointer for the sake of simplicity. And then there's a null pointer. So you've got a PTR1, and then you get this PTR2. PTR2 is array plus 20. I mean, this is just out of bounds, right? I mean, the array's got 10 elements and you're incrementing by 20. So it's an invalid pointer. And then you have a null pointer. In this case, I've got an integer pointer that I'm explicitly pointing to null. You'll see the use of it at some point. But just keep this in mind that these are the two types of pointers, null and invalid pointer. So we did talk about pointers a lot. What do you think, in your mind, would be the advantages of having a pointer? Pointers reduce the code and improve performance. They're used to retrieve strings, trees, data structures, basically. And then they allow us to return multiple values from the function. Pointers also allow us to access a memory location. I think the main thing is the accessing of the memory location. That really gives you the power to do whatever you want with the variable. And by having this void pointer, so you'd have to give it a type. So you can have this generic type. That also adds advantages to it. I don't really have any disadvantages. I can't really think of any. If you do, let me know. Email me. I wish the book didn't really call this interface because um, so it talks about the interface. Interfaces are available in Java, okay? They're available in C Sharp, but they're not available in C++, okay? Um, but the concept of interfaces is there, right? So you can't really say interface and give it a name. Um, but conceptually, interfaces are nothing but a way to describe the behavior of a class without committing to the implementation. Um, so what you're telling the reader or the one who gets the interfaces, these are the methods, this is how the class is going to behave, this is the input and this is the output, without actually having the implementation of those functions. So conceptually, that's what it is. But the keyword interface does not exist in C++. You should not use it. Uh, know the concept, but when we talk about Java or C Sharp, you'll have an actual keyword called interface. In C++, interfaces are also called, well, in what I should say is, I shouldn't say they are also, but I should say they're called pure abstract class. Now, pure abstract class is a unique type of class. In it, you have a pure virtual function and other functions along with it. Um, Now, what is a pure virtual function? A pure virtual function is a function that doesn't have an implementation at all. So by from a code perspective, you'll have the keyword virtual in there, and then data type, which is the return type, the function name, and you'll say equals to 0. Um, the keyword virtual, you might know of it as the reason why you have this keyword virtual is any class that derives from this base class is going to have access to it, and it can extend it, it can add to it, it can change the behavior, whatever. But in this case, the abstract class didn't have any implementation whatsoever, so the derived class are going to implement it. In order, and some of the key things with abstract class you should know is what will make a class abstract. An abstract class is a class that's specifically designed to be used as a base class. That should be quite obvious, right? Because since it has a pure virtual function, you compile it by itself, or you try to run it and you try to use it, the compiler is not going to know the implementation of it. The abstract class must have at least one pure virtual function, so that uh, this right here equals to 0. Virtual some return type, name of the function, can take in parameters, it cannot take in parameters, it's fine either way, equal to 0. And the same thing for the return type, it can be void without any parameters, but the virtual and equals to 0 ought to be there. And the derived class of an abstract class must implement all the pure virtual functions. Otherwise, it's not going to compile. Okay, so this is a key concept here. We're using abstract class as an interface, although interfaces don't exist, but the concept exists. The concept of abstract class exists. Pure virtual functions, those are useful, those are important, so get used to them. Um, So the rules for the interface, or the concept of interface, declare only pure virtual functions. Okay, so what this slide should say is it's the rules for the abstract data class. It's got only pure virtual function in there, no implementation whatsoever. So all of the methods equal to 0. And you cannot create an instance of an abstract class, right? Because the compiler is not going to know the implementation of the virtual functions. We can create a pointer to the instance of the derived class with a reference of a base abstract class. So pointers can be used, right? But the pointers are really going to be pointing to derived class. Let me walk you through a couple of examples here. So I've got a class CFG, and it's got a public method in there, virtual string return string equal to 0. Okay? This is a pure abstract class right here. Because it fulfills the conditions. The main condition being all the virtual functions equal to 0. In this case, there's only one virtual function, and that's equal to 0. Do we have any other? Let's go through them. Can I create an instance of CFG? No, I cannot, because it's a pure abstract class. Then I've got a child class um, that derives from it. It doesn't need the keyword virtual, but it needs the exact signature. And now instead of equal to 0, you're gonna have you're gonna return something. You're gonna have an actual implementation. So here I've got a child object and a base pointer. So you can have a base pointer point to a derived class. That's what's happening here. Now what you couldn't do is you couldn't say object CFG. So it doesn't know about CFG. The class, oh, GFGs. Why wasn't the object declared? Because it's got a pure virtual function in it, so it doesn't know its implementation, so you cannot have instances of an abstract class. Let's go through another example here. So here I've got um, a class website that's pure virtual, that's abstract. Um, so you've got a virtual string get name equal to 0, and then I've got a short form class and a full form class that derives both from website. Now, if it's deriving from website, what it has to do is it has to implement get name, get name, get name. And in the driver, I've got two objects, right? Short form, full form object one, object two, and then I've got a website pointer. Website is base class. So we got a pointer to base class. First I say, I point that to short form class, and then I call get name. And then I point that to full form class, and then I do the get name. Watch this. What happens? When I do short form, it does GFG. Which is this one right here. When I do full form, I do get name. So when you're using, one thing to keep in mind is when you're using pointers with classes, have the pointer point to the base class first, and then you can have it point to any base class. Food for thought. Try to have it point to the base class, derived class, and then see if you can change it from the derived class to the base class. If it's going to help or not, but this is just food for thought. The other thing is, the book talks about the header file and the implementation file. What you can do is all of the class header, um, just the names of the function, you can have them in the header file, and the actual implementation of the function in a implementation file, which is .cpp. And what happens with it is the book has references the date class, right? So it's got a date class in here. This is the date.h file, and it's only got forget about the explicit word for now. Uh, std string toString. So it's got a toString method that returns string, and it's got 3 private variables. And in your .cpp file, you will have return type, and then you will use the name of the class and the scoping operator. You see these 4 dots right here, and then toString. Because in the .cpp file, what's going to happen is you'll have to tell the compiler the name of the class whose implementation you're implementing. So if you just say string 2h, it's not going to work. You'll have to explicitly say which class does toString belong to, and that's what the scoping operator is. And then if you're on the Unix box, you do compiler g++ space. What happens is the header and the CPP file are compiled by one person, and then they're used by the driver that could be a third function. So once you compile them, you might get compilation errors or linking errors. If this were a lab, I'd show you the compilation and linking error. But then you'd say, well, maybe, we can just use Visual Studio, so I don't have to deal with the linking and the compilation error. Well, the compilation errors, yes, but the linking would be slightly easier if you're using an IDE. But nonetheless, that's how the scoping operator works. And then in Unix, there's a command to compile all the 3 of them together. Um, one thing I forgot to mention is in the last lecture I was talking about pointer, but one thing I didn't cover is I don't think I did was a constant pointer. A constant pointer can point to a constant variable, but a constant pointer uh, cannot point to a non-constant variable. Uh, but a regular pointer can point to a regular variable. But a regular variable. So this is something really important, right? Because if you think about it, why would you use a constant pointer? You would use it because you cannot change anything for it, right? Uh, like initially, if you're made that pointer point to something, later on you cannot change your mind and say, okay, now I'm gonna have it point to something else. So this is one uh, key thing to keep in mind. So I thought I'll mention that. Let me walk you through some examples of these constant pointer, right? So I've got two integers here, high and low. High is equal to 100, low is equal to 66. And then I've got a const pointer called score, and that is equal to high. Okay? So then, what is score pointing to? I output that. And then when you try to change score to low, I was thinking this is going to give you an error um, because value stored in score cannot be changed. Try this out on your compiler and see if you get this error. Um, right? Actually, let me just try it. Yeah, it is giving an error here too, so that's good. That's what I thought. Because this is a constant pointer, and then if you try to point it to something else, it's going to give you an error. Assignment of read-only location. But you can make it point to a different place, right? So here, the contents um, of what's stored in that memory is not allowed to change. But you can make the pointer point to something else, right? So there is a difference. So look at the syntax. Const int pointer score equal to ampersand high. Okay, so it's pointing at 100. So it's got a memory address that holds 100 in it. Um, but but if you make that same memory address store something else, that is not allowed. However, you can make it point to a different memory address, right? Content versus what it's uh, the memory that is pointing to. These are the two key differences that you should take away. It is confusing. I have two more examples. Hopefully that should illustrate things for you. Because this is allowed and that's not allowed. This is allowed because you made this pointer point to something else. That's not allowed because you're making the contents of the memory something else. Watch this. This is a different way of initializing, which is the same. So you can say A equals to 90 and B equals to 50, or do it in parentheses. And this is a way of making pointer point to ampersand A in parentheses. This is literally the same thing as doing this. Yeah, 2 equals to something like this. Right? There's exactly the same thing. But just to illustrate to you that this is also acceptable. So I've got a const pointer, and then I say, what are the contents of PTR? And what's the memory address that is pointing to? and then whatever it's pointing to, so it's got a memory address, the contents of that, I change it to 56. But if I make the pointer point to a different memory address, that's not going to be allowed. Watch, everything runs fine right now. Right, so PTR had 90 in here. Here, I change the contents of PTR to 56. And it was pointing at the same memory address right here. See, both of these memory addresses are the same. But if you really try to make this PTR equal to ampersand B, that's not allowed. Last time, you couldn't do this, right? But you could do this. Here, you can do this, but you cannot do this. Const was before int. So that's the key difference, the content of and what the pointer, which memory location the pointer is pointing to. Now here, it's a constant pointer to a constant integer, okay? I've got a const int, const b, const int pointer, const. So that, you see how the syntax is slightly getting changed? Const before the int. Const after the int. Const before and after. Now in here, you won't be able to do either or. You would not be able to change the contents of it, nor can you make the pointer point to some other memory location. You can only have PTR point to a constant pointer. You try to change the contents of this. It's not going to let you do it. How about, can you make the pointer point to a different memory location? You cannot do either. So this is a unique pointer. It's a constant pointer pointing to a constant variable. Okay? Try out a few examples. I know this is really confusing. And let me know if you have any questions. That's it for today. Take care.